Okay, so our big goal today is to talk about these two key terms, momentum and impulse. First of all, let's go ahead and define momentum. I would define it as moving mass. So that's the definition. The equation, we've got momentum, and it starts with an M, and M is already used for mass. So if you start going down the alphabet, you get to N. Capital N's used. What do we use capital N for? Newtons. Lowercase n, chemistry's got that. It's like number of what? Do you remember? Yeah, moles. Yeah. So that's taken, and then you keep going down, you get O. Well, it looks like a lot like 0, right? We can't make that a variable. Then you get to P. P is momentum. Capital P is already taken for power. Momentum is lowercase p. And we say moving mass. So mass is important. Momentum is equal to mass. And then what's the variable we use to represent moving? Velocity. So it's mass times velocity. And that's our equation. You can't really get a simpler equation than that. P equals m times v. Okay, the really only tricky thing is remembering that this lowercase p stands for momentum. Okay. Units. Let's think about the units here. Momentum as a concept is a very important concept, but it's not something we calculate a lot. So the units, it doesn't have its own units. What's the unit for mass? Kilograms. So grams in chemistry, kilograms in physics. What's the unit for velocity? Meters per second. So it's a kilogram times a meter divided by a second, and that's the unit for momentum. Does mass have a direction? No. Does velocity have a direction? Yes. Because velocity has a direction, we say that momentum is a vector quantity. Direction matters. Any questions about that part? That's our first key term today, momentum. Second key term is impulse. So let's start the same way. Definition. An impact force applied over some time. Impact force applied over some time. This word impact means it's hitting, or there's some sort of collision. If you look at that definition, there's two key terms in there. There's a force and there's time. So our equation is also a very simple equation. Impulse, the variable that represents impulse is a capital J. I know we use capital J for joules, but we also use it for impulse. And that's equal to, well, force and time were the important pieces here. Force multiplied by time. So impulse is force times time. Units. Well, what's the unit for force? Newton. What's the unit for time? Seconds. So it's a Newton second. So no new unit. Questions so far? Okay. Last thing is the impulse momentum theorem, and that just means that we need to combine these two ideas, momentum and impulse, into one big idea. We actually know the equation already, but we're going to have to write it just a little bit different for this unit. We're going to start with Newton's second law. Newton's second law stated that the net force acting on an object is equal to the mass of the object times the acceleration of the object. So net force is equal to mass times acceleration. I want to substitute acceleration. I want to come up with something else that I can put into there. Think motion equations. Because if I look at these two equations, momentum and impulse, I don't see an acceleration in there. And my goal is to come up with an equation down here that relates these two. So anyone know a motion equation? It's actually the definition of acceleration that I can substitute in. What is acceleration? It's the change in... Those are the two variables that matter, velocity and time. It's the change in velocity divided by time. Okay? So what I'm going to do is substitute that in. So instead of A, we'll say force is equal to mass times that V final minus V original, that's your change in velocity, divided by time. Okay, so it's the same equation, but now I've eliminated acceleration because that's not part of my big idea today. Impulse is force times time. Any way to write this where I have force times time? Anyone see a way? Here's force. I need force times time. Okay, you see the time down here? If I just multiply it across, so let's come over here. If I multiply it across, force times time equals mass times that change in velocity. So V final minus V original is change in velocity, right? What's mass times velocity? Yeah, momentum. So what do I have here? Impulse is equal to mass times change in velocity. That means that impulse, force times time, is equal to the change in momentum. Because mass doesn't change, but the velocity changes. So change in momentum. What's another way we could write this? We could say force times time is equal to the mass times the quantity V final minus V original. So if you like that way better. There's a lot of different ways to write this idea. But the big idea states that when you apply an impulse to something, it changes the momentum of that object. Any questions about this before we give some examples? No questions, everyone's good. Okay, so I've got 3 examples I want to talk about today. The first 2 examples are going to be stopping examples. We're going to talk about an object stopping. So what stops? I want to relate this to your lives as much as I can because this unit has a lot of relation to your life. What was that?
When you throw your phone at your sibling, it stops on the forehead.
Oh, that would be a pretty abrupt stop, and it might, I don't know, it might hurt the phone. I don't know about your sibling, but it might hurt your phone.
That would hurt my forehead.
How about we talk about stopping in a car? Because you've all had to apply the brakes at some time in your life. So right now, I want you to picture yourself in the driver's seat of your car. Okay? So get this in your brain. Make sure your cell phones are put away. Make sure you're awake right now. Picture yourself in your car sitting in the driver's seat. You got yourself there?
Yes.
Okay, now you're going to be driving on the road. So picture yourself driving down the road, I don't know, about 30 miles per hour. Okay? In the distance, decent distance, you see a stoplight and it just went from yellow to red. Okay? What goes through your mind? Faster. I hope not. You're thinking, I got to start stopping, right? I got to slow down, so I stop at the red light. You're shaking your heads, yes. So you're in your car, you're traveling down the road about 30 miles per hour. You see the red light coming up. What do? You start moving your foot off the gas pedal and onto the brakes. Okay. Now, how are you going to push on the brakes? You going to jam the brakes on, or are you just going to lightly start pressing on them? Okay. So you know you've got some time. You're making a very controlled stop, slow, gradual, controlled stop. You know, we're not in a hurry, and we know the red light's ahead of us. So you got all that in your brain. Here's my equation. Force times time, impulse, is equal to change in momentum. So let's look at the right-hand side first. And this is the stoplight stop. So a nice, controlled, leisurely stop. I want to look at the right-hand side of this equation first. We've got mass times V final minus V original. Okay? Well, the mass of your car is just some m. Yeah, mass. What's your V final going to be? 0, because you're stopping. Good. And you were moving at some V original, like 30 miles per hour. We're just going to put V original, but it's some quantity, some reasonable amount. Okay? What made you stop? Your brakes did. You applied a force. Over some nice long time, that entire time you had your controlled stopover. I would say that this is a fairly large time to apply your brakes. Think about all the different times in your car you would apply your brakes. I'd say this scenario is one of the larger time lengths. Everyone agree? Okay. So a big time. Well, I'm going to write that as a big T because it's a big time for you. Okay. And if you think about the amount of force that your brakes are applying to the car, it's a reasonable amount of force, but it's nothing huge, right? Compared to other times you might apply your brakes. So what I'm going to do is use a smaller F because it's not a huge force. Okay? You're just applying a gradual force, slowing down over some time. So you applied a force with your brakes over some time, and that changed the momentum. It went from some momentum with V original to no momentum at all. V final 0. Everyone good? Okay. Let's give a different scenario. Okay, you're on the same street, traveling at the same speed at 30 miles per hour or so. It's a pretty open area. There's not many cars around. There's really no one behind you. Suddenly, a playground ball rolls out in front. Okay? What do? You hit the brakes. You don't just gradually press the brakes. You slam on those brakes because what's going to come after the playground ball? A kid. Okay? Now, maybe the kid won't. Maybe the kid's smarter and they can stop themselves, but most likely there's a kid that's going to come out after them. Okay? So you're going to slam on the brakes and you're going to do what? Your car is going to do what? It's going to stop. Okay? Just like it stopped at the stoplight, your V final is going to be 0. So now we have the playground ball stop. So playground ball rolls out in front of your car. Let's talk about the right-hand side of this impulse momentum theorem first. V final is 0. The mass of your car didn't change. You were traveling at that same speed before you slammed on the brakes. How long did it take you to stop? Nice long time? No. Tiny time. You were trying to stop as quickly as possible so that you could keep from hitting the kid that might be running out after this ball. So how much force did your brakes apply to your car? A lot. Big, huge force over a little bitty time. Okay. Here's my question to everyone. I want you to answer it silently in your heads first. Which scenario had a bigger impulse? The stoplight stop or the playground ball stop? Which scenario did you apply a bigger impulse to your car? You know I like to ask a lot of trick questions.
They are equal.
Absolutely right. Why are they equal? Look at the right-hand side of these. I don't want you to look at the left side. That's impulse. If that's impulse, isn't this change in momentum also the impulse? Okay? Do you see anything different on the right-hand side? No, it's the same impulse. It's the same change in momentum. Now, these products are the same. Force times time, force times time. What's different about these two scenarios? Units are the same. Yeah. So if it's a big time multiplied by a little force, or a little time multiplied by a big force, The forces are dramatically different, but the result is the same. It's the same impulse. Now, the impact force is different, but the impulse is the same because the change in momentum is the same. Does everyone see that? We watched a video last time and saw something with an egg. Which egg is this? The sheet or the wall? Sheet. And this would be the egg hitting the wall.
So does that mean you would hit your kid?
Huh? Well, it depends. Hopefully not. But it is amazing how fast the kids can be in front of your car. And you're doing the best you possibly can, and still horrible things can happen, even when it is horrible. But that's why we think about these things all the time before you might be in that situation, so that you don't have to think very much in that situation. You just react instead. So, because that would be not only a horrible thing for that kid and that family, but you also would have just a horrible time afterwards. Okay, last one. Third one is different. So this is a totally different scenario. Third one, I'm not looking at a stopping momentum. So why do we look at the first two? Because there are different ways to stop. But the impulse, the impulse is the same for all these stopping scenarios. It's just different makeups of force and time. The next situation I want to talk about is some sort of bouncing situation. Okay? And so if I drop this pool ball, oh, that didn't bounce very well. Okay? This lab bench didn't give very well. And what happens if I drop a ball of clay? So this pool ball did a nice bounce. Okay. Nice elastic bounce there. What happens with the clay ball if I drop it? Yeah. Most of you can't see it, but it just flopped to the floor. So it just stuck to the floor. I want to talk about the impulse that both of these objects experienced. Okay? The floor is applying an impulse, force over some time to both objects. The clay ball sticks when it hits the floor, and the pool ball is dropped.
Did you hit anybody?
No. Ramon almost got hit. The coat stopped it. And the pool ball bounces. So in this last one, we're going to have two classifications. In the third example, the clay ball and the pool ball. Let's just come up with a hypothesis on your own right now. Are the impulses that these two experience the same, or is one bigger than the other? So right now, to yourself, look at those two scenarios before we put any numbers or other further ideas in. And just on your own, decide. They both experience an impulse. The floor applies a force over some time to both balls. Decide if it's the same impulse, like in the first two examples, or if there's differences. Okay. Do you need to take a little walk around the room or go get a drink? Okay. Okay, has everyone got it in their heads?
Yes.
No sitting on the fence now. Okay. So I'm not going to make you announce it. This is your own thoughts. Let's see how well thought out you've got it. So we got both balls. Let's say we drop them both at the same height. What could you say about the speed at which they hit the floor if I drop them both from the same height?
Same.
About the same, okay? They're about the same size, so the air resistance is about the same. The mass is about the same also. So we're going to say both have the same mass. So when they hit the ground, they both have the same speed, they both have the same mass. One, though, has a final velocity coming up, and then the clay ball sticks, so its V final is 0. Good? Okay. So let's put some numbers and some ideas down then. Let's not worry about the left-hand side yet. Let's worry about the right-hand side. So it's mass times change in velocity is the change in momentum. They both have the same mass. So the clay ball has some mass m. The pool ball has some mass m, right? And it's the same mass, so I can just use m for both. Clay ball. V final minus V original. V final for the clay ball is 0. It's stuck to the floor. minus the original. They're both going to be hitting the ground somewhere close to about 6 meters per second. So can I put 6 meters per second here?
Sure.
Okay. So v final minus v original is the change in velocity times the mass is momentum. Now the pool ball, it has some v final. Let's put in the v original because it's the same v original, right? Now notice up here I used a positive v original. So I just arbitrarily decided its v original was positive and that was going down. And so the pool ball rebounds up, so that would have to be what kind of sign for that direction up? Negative, okay? And I know that's a little bit different, but we're okay with that. It's going up, and it doesn't quite reach my hand. So if I drop it from here, it didn't quite reach my hand. So is it leaving the floor as fast as it hit the floor?
No.
No, a little less, right? I don't know, can we just... 3? Okay, we're going to say 3 meters per second it left the floor with. So we said that's negative, right?
Yep.
Because it's coming up and that's the opposite direction. Has to have the opposite sign. Everyone good? Okay. Do they have the same impulses? Do they experience the same impulse? Just look at this. No. Minus 3 minus 6. That change in velocity would be a negative 9. What's the change in velocity up here? Negative 6. The negative doesn't tell you bigger or smaller. It just says a direction. What direction was negative, up or down?
Yeah. Way up.
Up in this case. So what direction is the impulse? It's pushing up. Does that make sense? The ball comes down. What direction does the floor push on it when it hits the floor? Up. And then to get off the floor, what direction does the floor have to push on it? Up. Okay? So why is the impulse of the ball, the pool ball that bounced, greater than the impulse of the clay ball? Because the floor had to push on both balls to stop them. But then the floor had to apply more force to the pool ball to push it off the floor. So it's a greater force. Time-wise, I don't know. Was the impact time the same? Was the clay ball a little longer? I would argue the clay ball's impulse time was probably a little bit larger because the clay squished as it hit the floor, and in squishing it, that was an increase in the impact time. So I would say that it's a little bit bigger time for the clay ball. Not a whole lot bigger, but probably a little bit larger. And then that means that the force for the pool ball had to be quite a bit larger. So I maybe even drew it too small. Maybe it needed to be even larger. So how have you experienced this in real life? If you play any sport that includes a ball, if the ball hits you and bounces off of you, it's going to hurt more than if it hits you and sort of sticks or sort of falls straight down. And that's maybe something you've experienced. If you've ever played paintball, anyone in here ever gone paintball? Yeah, okay, so about half of you have experienced this. What happens when the paintball doesn't break? Can you picture that? Some of you just, ooh, you got that face that look, ooh, that hurts. It hurts. If it bounces off of you and it doesn't break, it hurts a lot more than if the paintball hits you and splats. And this is why. Because your body is having to apply a force to that paintball to stop it, and then it's having to apply even more force to push it off of your body. And whatever force your body is applying to the paintball, Newton's third law, the paintball is applying the same force to your body. So it's a much bigger force. If it splats, think about how much impact time that would be for the paintball to break apart and splat. That's a huge time compared to the bounce time. So it's a much, much smaller force. But no matter what, the impulse required, the change in momentum for a bounce, is always much, much greater than if something were to hit you and stick. So if you have a collision, do you want your cars to bounce or stick? Stick. You don't want to bounce. So not only did the old cars in the 70s, 60s, and 70s were they made out of really, really strong material that didn't take any crushing. You could drive them away if the driver could drive them away. So they didn't crush. So there was no way to increase the impact time that way. Those cars were so strong, they bounced off of one another. They bounced off of one another. The force then is going to be even bigger because of the bounce. So super, super unsafe cars they used to have. The video was a little misleading. Can one car experience more force than the other car can? No. Both cars are experiencing the same amount of force. There was one statement in the video that I wasn't just pleased with. They had a misleading statement. So both cars do experience the same amount of force. But we know that the same amount of force, at least with different materials, can create different amount of damage. Okay. Are there questions about this? Okay, let's try a few example questions. I think you will be pleased with these example questions. The first one, part A. A baseball of mass 0.16 kilograms is moving at a positive 35 meters per second. Why did they take the time to put a positive there? It's because momentum is a vector and direction matters. What is the momentum of the baseball? Take 30 seconds right now. Find your givens. See what kind of givens you can find. Write them down, please. Okay, so I read through here. Baseball mass is moving at this speed. So they've provided us the mass, 0.16 kilograms, and the speed of 35 meters per second. Our unknown is momentum. We are following our guess steps right now. The equation we have then that relates these three variables is momentum equals mass times velocity. I'm up to my fourth step. I need to solve the equation, but look, it's already momentum equals. I don't need to do that. So we substitute our values in. 0.16 kilograms times 35 meters per second. And if you plug those in, I think you're going to get 5.6. Let's look at the units. Again, there's no special unit here. We have kilograms, meters over seconds. So it's 5.6 kilograms times meters, all divided by seconds. Questions? Yeah, pretty straightforward. Go ahead.
On Quest, will that be what we have to put in as units?
You don't have to put any units in Quest. It tells you what the unit needs to be, but then you just substitute the numbers in. We won't actually have a Quest for this unit, but I will give you a Quest for the whole semester at the end. This unit's short enough that we're not going to have a Quest. We will when we do electrostatics next time, though. You want to make a circuit? We will eventually, yeah. I think it's fun. I think you'll like it. Next one, find the velocity at which a bowling ball of mass 7.26 kilograms would have the same momentum as the baseball. You need two givens. Find those two givens and write them on your paper right now. Two givens, one unknown. Find your two givens. So one given is stated right here in the question, the mass of the bowling ball. So a bowling ball is much larger than a baseball, has a much larger mass, 7.26 kilograms. And it says we want to have the same momentum for this bowling ball as the baseball had. So you're going to take that momentum that we found in part A and use that as the momentum of this bowling ball in part B. Okay. And they're asking us for the speed of the bowling ball. So take a moment before we start solving this. Would we expect the bowling ball with a much larger mass to have a greater velocity than the baseball, an equal velocity as the baseball, or a smaller velocity as the baseball? Class, what do you think? Smaller. So it is going to be smaller. Why? Because we want the same momentum mass times velocity to give this. If it's a much bigger mass, then the velocity has to go down. So if one goes up, the other has to go down to get to the same. Okay, equation, momentum equals mass times velocity. Solve for your unknown velocity. Velocity equals momentum divided by mass. Substitute those values in, and we have 5.6 kilogram meters per second divided by the mass, 7.26 kilograms. Kilograms are canceling out. We're going to get meters per second, which is velocity. It's going to be nice and small. 0.7 something. What do we get? 77? Okay, so 0.77 meters per second. Questions? Backside. Okay, this is just a little bit harder. We now have a baseball. Different mass, but still a baseball. It's pitched at a positive 38 meters per second. After it is hit by the bat, it moves horizontally at a negative 38 meters per second. So you've got the pitcher's mound out here. The pitcher is out here. They throw the ball. And then we have the home plate over here, and we have our batter.
You're like the cat thing.
A cap? Oh boy, you might be going beyond my ability. There's my little cap. Okay, the ball's coming at the batter. The batter hits the ball. What direction does the ball go? Back towards the batter, the pitcher. Oh my gosh. Pitcher, because the catcher is behind
That is
the
the
batter,
pitcher.
right? Okay, so there's our batter. He hits the ball, and it goes back towards the pitcher. That's why there's a negative velocity for V final. Okay. So, givens. Mass, 0.144 kilograms. V original, the pitcher throws the ball at a speed of 38 meters per second towards the batter. When the batter hits the ball returns towards the pitcher. In this case, it's negative 38 meters per second. We had some softball players yesterday, and they said usually it travels just a little bit faster back. Others of you are nodding your heads too. So, okay, everyone's nodding their heads. Very good. Part A, what is the impulse? So here's my unknown. Who's got an equation? Impulse equals force times time. Great equation. Only problem is, do my givens match that equation? No. Okay, let's go hunting again. Is there anything else we can say about impulse? Impulse equals change in momentum. Momentum is mass times velocity. Does that match these? Yeah. Okay. So that would be mass times the change in velocity, V final minus V original. Are we comfortable substituting in then? So impulse equals the mass, 0.144 kilograms, times V final, which is negative 38 meters per second, minus V original, the positive 38 meters per second. Now, there is a knee-jerk reaction when you see two numbers that you're subtracting to immediately say, oh, they cancel out to 0. Is that the case here?
No.
No, it's not. They actually add because we have a negative minus a positive. Okay, so really check out those numbers before you have that knee-jerk reaction that says it should be 0. And I'm getting negative 10.94. Yeah? So negative 10.94. Unit-wise, because they're talking about impulse, I'm going to say newtons times seconds. But if I look at the units up here, that's a kilogram meter per second. So where does that come from? Let me prove something to you. If I have newtons times seconds, what's the units for newtons? Force is mass times acceleration, so mass is kilograms. Acceleration is meters per second squared, and then multiplied by seconds. What happens to seconds? One cancels. What am I left with? A kilogram meter. Oh. Units for momentum, kilogram meter per second, the same unit as a Newton second. So does it really matter which you write? No, they mean the same thing. Okay. We will leave it as a Newton second for now. Questions about part A? Part B. If the bat and the ball were in contact for 0.8 milliseconds, what was the average force the bat exerted on the ball? So I see a new given, time, 8 times 10 to the negative 4 seconds. That's 0.8 milliseconds, so really small time. Makes sense. We are looking for the force. So in part A, we used change in momentum. Now in part B, can I say impulse is force times time? So if impulse is force multiplied by time, and I'm looking for force, I need to divide the time. I have all of those values, so I substitute them in. The impulse from part A was negative 10.94 Newton seconds divided by the time, 8 times 10 to the negative 4 seconds. Want everyone to try this on your calculators. Before break, we had a question where you had to use scientific notation on your calculators, and not everyone was showing that they were comfortable doing that. I know that you've done this in chemistry, but try it again. Make certain that you can get to the same answer as everyone else. So on your calculator, if you're using scientific notation, you are looking at this button right here, this EE button. Okay? So it's 8, the times 10 to the, is all that EE button, and then negative 4. So that's what it should look like on your calculator. So I'm getting negative 13,675 newtons. Make sure you're getting that on your calculator also. Yeah, you use this button right here. When you press that, it gives you the E right here. And that's the scientific notation for your calculator. So right there, that means the same as this. So negative 13,675 newtons. Anyone having troubles with their calculator for this?
That's what I thought.
Well, because you got the times 10. Use the E. So negative. Negative 4. There you go. Just you see how it works. Anyone else want to look at how the calculator handles this? Okay, so that's part B. Part C, it says find the average acceleration of the ball during its contact with the bat. So my unknown is acceleration. They're not giving me any more givens. I have everything now that I need. There's actually 2 ways to do this. Someone come up with one way to find acceleration. What's one way? Motion equation. How about V final minus V original divided by time? Do we have those givens? Thank you. Yes, we do. V final is a negative 38 meters per second minus V original, which was positive 38 meters per second, divided by the time, which is the small time here, 8 times 10 to the negative 4 seconds. Plug that in your calculator. Let's see what we get. I'm getting about negative 95,000 newtons, meters per second squared. What's another way? How about net force? Acceleration equals force over mass. What was the force? Here's the force. Do we know the mass? Sure, let's try that also. So that's negative 13,675 newtons divided by the mass, 0.144 kilograms. Doesn't that round to be the same thing? Negative 95,000 meters per second squared. Okay. So 2 ways to get to the correct answer. Which way you take is up to you. Both work just fine. Okay, here at the end, part A. Is the momentum of a car traveling south different from that of the same car moving north at the same speed? Same car, same speed. One's going north, one's going south. Talk with people around you very quickly right now. What do you think? Come up with a consensus for your table. Do they have the same momentum or do they have different momentums? Okay, what do we think? Same or different? So mass times the speed, they get the same number, right? But one's north and one's south. Does the north and south matter? Yeah, it changes direction, and direction, does it matter for momentum? Yeah, because it's a vector quantity. So one would be a positive, one would be a negative. They would both have the same magnitude, but one's positive, one's negative. So I would say no, they don't have the same because of the direction. Write down whatever you need to remember about this. B, if you jump off a table as your feet hit the floor, you let your legs bend at the knees. Just picture it, jumping off the table and landing straight-legged. Yeah, so you just got a bad feeling in your head when you thought about that, because it would hurt. Why do we bend our knees when we land? Okay, so what is this? This is, at the beginning, this is one of those stopping ideas, right?
Yeah, impulse.
When you stop, your impulse is the same. No matter how you stop, your impulse is the same. This force times time is the same as this force times time. We would much rather have this scenario, right? Large impact time, smaller impact force. The impulse you experience is the same, but that doesn't mean it has to be a large impact force. Okay? So you bend your knees, it really extends the time. You guys like to watch the movies. The hero jumps off a train, the villain jumps off a train. How do they land? They roll. What does that rolling do?
Distributes the energy.
Yeah, it takes that time to stop and really expands the time so that the force they experience is less. I have never personally done that kind of thing. I have to think that the roll probably doesn't fix everything. But from physics, we know that it would extend the time and decrease the force. Questions about part B? Okay, C. An archer shoots arrows at a target. Some arrows stick, while other arrows bounce off. Which arrows give a bigger impulse? So when we talk about the stopping questions, they're all the same impulse, whether you land with